Hi friends, today let's talk about SimCluster. It's an algorithm that powers many Twitter applications. So it generates universal embeddings for different entities in Twitter, including user, tweet, and topics. Let's get started. The goal of SimCluster is to build universal representation for different entities in Twitter. Those entities including users, tweet, and also the topics. Because of the volume of data of Twitter, SimCluster was designed to be scalable. So this is a product perspective. They want to have a universal representation of different entities in Twitter that are interpretable. For example, with tweets, SimCluster should be able to generate embeddings that can compare different kind of tweets, and that embeddings should be able to measure the similarities between tweets. And similarly, the embedding distance between different entities should also measure their similarities. That's the requirement for those representations to be interpretable. In addition, because the volume of the Twitter data, the SimCluster has to be designed to be scalable. So how did they achieve this? To build a scalable and universal representation using SimCluster. There are two stages in the SimClusters. So stage one is basic this part, and this is stage two. After stage two, you'll be able to power these applications. As you can see from stage one, it's kind of confusing here. Stage one actually you didn't use those graphs. Those graphs are for stage two. And for stage one, you actually only use this part. So stage one is basically taking input as a user graph, and then it generates the user interest representations. Basically, after these steps, the goal is after stage one, you have a user representation. You can see it as a sort of embeddings for the user ID. And then in stage two, you have those different kind of graphs. This is user graph. This is user tweets graph. So they are also like two bipartite graph, and you use your user embeddings to represent these entity embeddings. And lastly, with these newly generated entity embeddings, you'll be able to power the applications. So to summarize, stage one, we got the user representations, and stage two, we use these and for stage two, we use these user representations to generate the entity representations. Now let's focus on stage one. So stage one starts from a bipartite graph. You can think about this. This is the input of stage one. It has user, follow, creator. And with this graph, stage one had 3 steps to generate user embeddings. Step one is that it converts this bipartite graph into a unipartite graph. And step two is that from this unipartite graph, step two is able to generate representations for the creators. For step three, we have adjacent matrix, we have the creator embeddings. We leverage them both to generate the user embeddings. Now let's focus on step one. Step one takes the user-to-user graph and model it as a bipartite graph, where the left-hand side are consumers and right-hand side are producers. So why are they doing this? There are 2 reasons. First of all, in a social media platform, there are always more consumers than producers, and the gap is large. If we can focus on the producers and get their representation, we'll be able to use those producers' representation and then express the consumers' representation. The data scale of producers is much smaller than consumers, so comparably, it's an easier way to solve this problem. So the first benefit is the smaller scale. And second of all, it's expressiveness. So by viewing this as a bipartite graph, you can differentiate the communities that user has influence in and the users are interested in. So this starts from this adjacent matrix, as you can see here, where the rows are the consumers and the columns are the producers. If they have previous engagement or there's follow relations, then will be annotated by the binary code here. With this, they calculate the cosine similarity between different producers and then generate the similarity graph. So this one is a bipartite graph, and this one generates a similarity graph only for the producers, which are much lower scale. So if you're curious of how this cosine similarity is calculated based on the vector similarity, as you can see here, V1 is 0, 0, 1, 1. V2 is 1, 0, 1, 0. When you get the cosine similarity, you got 0.5 here. So as you can see here, it is using the follower vector to compute the similarity between the two producers. So to recap, step 1, the input is a bipartite graph, and the output is a smaller scale unipartite graph that only has producer entities. Now let's talk about step 2. So step 2 takes this unipartite graph and get the representation for the producers. So as you can see here, the rows are the producers and the columns are the communities that SimCluster returned to represent this producer. So how do we do that? First, it's to define an objective function. How do you know your community assignment is good? So this objective function quantifies this. The community assignment, what it's saying that if you look into all the edges from the unipartite graph, and from those edges, if you look into the left node and right hand side node and calculate if they have overlapping communities. And similarly, if you look into the producers that don't have an edge that link them and calculate how many overlapping communities they have. The objective function wants to reward this part where two entities, if they are linked by an edge, they have overlapping community. It wants to penalize this kind of function where if two entities are not linked by an edge, then they shouldn't have overlapping community. So that objective function is actually decomposable, so you can look at it, you can calculate it for each node. So the idea is that for each node, if you look into all the neighbor nodes and then calculate the overlapping, you can calculate the overlapping communities of this node versus this node and its neighbor nodes. And it can look into the rest of the node that doesn't have an edge with this node and then calculate the overlapping communities for the penalization, for the penalty. With this objective function, now we will know whether the community assignment is good or not. So we will use this objective function to measure the quality of community assignment. And to do this, step 2, use this algorithm called metropolis testing. So it is a bootstrapping method that keeps iterating. So it has essentially two important steps. First of all, if you generate an initial community assignment, and then if you keep iterating for the key epochs, and for each epoch, if you propose a new community assignment, and then measure how good is this new community assignment by calculating the objective function, which we just talked about. So if according to this new objective function, our proposed new community assignment is better than previous, then it will be accepted with a certain probability. This is to avoid the local minimum. So the original approach is that for both initialization and the proposed new community assignment, it is always random. So as you can see, if you always assign random, that will take very long for this algorithm to converge. That is why in Twitter paper, they propose some heuristics. So the change is mainly on the two important steps. One is the initialization, the other is the proposal function. So instead of randomly initialize, the heuristic they approach is that when they initialize the community assignment, for each community, it will randomly choose a producer node and assign all its neighbors as the same community. So when you think about it, it is a heuristic. This heuristic is assuming that for all a producer's neighbor node, they belong to the same community. So it's a one step ahead compared to random initialization. And second, it also applies some heuristics for the proposal function propose the next community assignment. The main difference here of this proposal function and the random proposal is that they apply two steps. First of all, instead of looking into all the community assignment, they only look into this node's communities. So this is one step ahead heuristics. And second is that they limit the scope by assuming that each producer can only be assigned to a max, that each producer can only be assigned to a max of L number of communities, which also makes sense because you don't really need to consider all the number of communities. As we summarize here, first of all, is NU. You only look at this neighbor nodes community when you calculate the new assignment. And second, it's limit the number of communities you look into. So with these two heuristics, the Twitter paper claimed that they're able to calculate the producer representation and unblock the scalability issue. So after step 2, we got a representation for all the producers, where the rows are producers and columns are the communities. And each row means that how associated we think this producer belongs to this community. The next step is to calculate the user representation. The Twitter paper does this by leveraging the adjacent matrix. So with this producer representation and the adjacent matrix, they calculate the user representation. So what they're arguing is that instead of producer representation, user representation can give whether the paper mentioned that compared to producer representation V, user representation is more dense. Now let's talk about stage 2. In stage 1, we now get user interest representation, and stage 2 tells us how to get the entity representation from the user representation. The key idea is to aggregate the user embeddings. For example, for certain items, you want to look into all the users who have engaged with this item and aggregate those user representation and use it to represent this item. So that their key innovation is that they talk about how they are able to do this aggregation in a streaming fashion with a special design decay factor. So the key idea of decay factor is that, first of all, there are two dimensions about the decay. First is how recent your item is. If you look at their formula, they use the decay factor to determine how much of the previous value we should retain. So basically, if the decay factor is smaller, it will not reserve any of the last value. So when you look at here, there are two dimensions of decay factor as we just discussed. One is how recent your new item is, basically how old your last item is. And second is that it's more fundamental. And second is more fundamental is your item by itself, by nature, very evolving and very much in change. As you can see, this half-life is similar to their shelf life. The longer the half-life, the bigger the decay factor. So actually half-life is in the positive relation with the shelf life here. It defines how much your item change. For example, here it thinks user recommendation change less, but for tweets and topics, those things should be constantly changing, and the stream update is more needed. So for tweets or topics, those items, they will have a smaller half-life, meaning if this item is too old, we will preserve less of the values by having a smaller decay factor. But if for like user recommendation, creator recommendation, those things rarely change or change more slowly, they will have a bigger half-life. That means we'll have a bigger decay factor and preserve the last value, even though it can be an older value. So with this decay factor, you cannot just keep adding on top of the previous value to get your new value. The design here is able to suit the Flink style streaming fashion so that you can keep updating the embeddings representations of your items. So this way, they're able to leverage the user embeddings and to represent the item embeddings. So as we just talked about, user embeddings are slowly changing, but item embedding can be changing really fast. So back to this figure, stage one can be doing in a batch job, but stage two, you can do it in a streaming fashion because of the business need. Let's talk about how Twitter use SimClusters. There are essentially two ways they're using it. One way is to use those representation as candidate source. So similar tweets, it leverage the similarity between two tweet representation. So they did it using ANN search. The other candidate source is from user to tweet. Because SIM clusters provide universal representation from different entities, including user, tweet, and topics. So you can calculate similarity between all of them, like tweet to tweet, topic to user to topics, and use them as candidate source. And the other way to use such kind of representation is to use it as the ranking model features. So as you can see here, for the who to follow models, Twitter added same cluster representation of both viewer and the candidate user. And they claim to have seen significant gains in this application. To summarize, there are two kind of applications. One is to build new candidate sources by using similarities between those entities. And second is to use as features in other engagement models. To summarize, SimClusters, this algorithm provides universal embeddings for user, tweet, and topics. It has two major applications. One is to as candidate source, and the other is as features for other models. The way Twitter do this is through a two-stage process. First stage, generate user representations. And second stage is to use those user representations to represent other entities, such as tweets and topics. With that, that's all about this paper, and thank you for watching.